Okay, I have 3 topics I want to review with you in the last 15 minutes of class. We should be able to get through those pretty quickly. The first, you'll need to be familiar with the idea of parallel and perpendicular lines. They will come up lots of times throughout the entire semester as they relate to calculus. There is another word for perpendicular that you may find, and it is called normal. Okay, so normal is not in this sense the opposite of crazy. Normal is a synonym to perpendicular. So when they say find the normal line, they're asking you to find the perpendicular. So they will often say find the tangent line and the normal line instead of using words like perpendicular. Okay? And so if you have the original slope, and the original slope of something is indicated as m, then the normal slope, which is the perpendicular, do you remember what the relationship is between the original slope and the normal slope, or the perpendicular slope? What was that? Say it again. Okay. All right, so we are going to, you're close. It is the multiplying by negative, that's part of it, but multiply, I wasn't sure what you meant by that.
Both slopes, so the first one.
Okay, all right, Holiday?
The negative reciprocal?
Okay, so the reciprocal too is key to that. So not just the negative, but the reciprocal as well. So we want negative 1 over m. And so depending on what the original one is, the normal or the perpendicular slope, sometimes they say flip and rip. Okay, flip the sign and reciprocal. Okay, the negative reciprocal is what we've got for that. So maybe an example of something you might have to do with that is to write a normal line to the existing line, 3 equals y equals 3x minus 4, through a different point. So maybe through the point negative 1, 2. So write a normal line to the existing line, but through a different point. And so what you would need to do is say, all right, identify what the slope is. And so you can tell pretty easily that the slope is going to be 3. And so the original slope is going to be equal to 3. And so that means the normal slope would be the negative reciprocal of that. So that's negative 1/3. Now to use that normal slope through a different point, you need to use the point slope form of a line. And the point slope form of a line is y minus the y value of the point, the slope that you're going to use, and then multiplied by x minus the x value of the point. And because we want to write a normal line, we'll do y minus, the y value is 2. That comes from the x and y coordinates. The slope we're using is negative 1/3. And then x minus the value negative 1, which ultimately would simplify to x plus 1. You do not need to distribute. You don't need to get y by itself. You can stop and leave it in that form. There's nothing wrong with going further. I'm just telling you you don't have to. Okay, save yourself a little work. You can just stop right there. Any questions on that one? Might be a little bit since you thought about parallel perpendicular. Okay, the second topic I want to talk about with you is the topic of an inverse. All right, so if we have a function defined as f of x, do you remember how to write the symbol of what an inverse is? Jason, do you remember that? How to write inverse? A little negative 1, right. Okay, that little negative 1 right there is the notation for how we would write an inverse. Okay, now how do you find it? That's how you write it, but how do you find it when you have a function? All right, so for example, suppose you had the function g of x equals 3x squared minus 7. Now that's a parabola. Anything with x squared in it is going to be a parabola. The domain of the parabola for all parabolas is going to be all real numbers. Okay, that's a script capital R is what I mean when I say all real numbers. You can write the words all real numbers. You could write the interval negative infinity to positive infinity if you like to write it that way. It doesn't matter to me as long as you know how to write something that means all real numbers. And the range of this, because it's a parabola, it helps me to picture the parabola in my head. This parabola, without looking at a calculator, I know it's a parabola that's going to grow upwards like this. Okay, because of the 3x squared is a positive number, so it's going to grow and face up. I also know that the minus 7 drops this parabola 7 units below the origin. So if I was picturing this in my head, I'd go 1, 2, 3, 4, 5, 6, 7, and I would know that the parabola is going to generally look like that. That helps me with the range. And so the range of this function is negative 7 is less than or equal to y. So y is greater than the value of negative 7. That would be the lowest. All right, now we want to talk about how to find the inverse of that. So the inverse of this function comes where you invert the position of the x variable and the y variable. And so instead of it being 3x squared minus 7, it's going to be 3 inverse squared minus 7. And then the x is on the other side. So you're switching places. That's what it means to invert something. So the inverse is now in the position of x, and x is now in the position of where the function is. And we add 7 to both sides. So x plus 7 equals 3 times the inverse squared. And we work on getting that inverse alone by dividing both sides by 3. So x plus 7 over 3 equals the inverse squared. And then we want to get rid of the square. So how do we do that? What do we do to both sides to get rid of a square? Luke? Okay, and what is included with every square root? Positive and negative, correct. So this would be the positive and negative square root of x plus 7 over 3, and that is the equation for our inverse. And then you might be asked to find the domain and the range for that. Okay, well the domain and the range are the inverse of the original domain and the range. So the domain for this one and the range are now the reverse of what they were before. So the range is now all real numbers. And the domain is now negative 7 less than or equal to, but it's x. Okay, yeah?
Would you mind if we did negative 7 to infinity, like the
Nope.
brackets?
Nope. So you could do negative 7 less than x up to infinity like that. Okay?
Is that fine?
Okay, good question. You're talking about interval notation, okay? And so you did negative 7, comma, infinity. And it would be right to do this, but because we're equal to 7, you would do a bracket, okay? And that is fine if you use that. I usually don't ever use that. I understand what you mean as long as you write it correctly. I don't typically use that because, I mean, say for example, somebody wrote this. How do I know if they're talking about the interval from negative 5 to 2, or if they're talking about the position of the coordinate point negative 5, 2 on the graph? Like, to me, that's why I don't use it, because it's out of context. You're never clear about what they mean. But if you write domain is, I'm going to know what you mean. Okay, so you'll never see me do it, but I have no problem if you do it that way. All right, thanks for asking that. All right, one other example under domain and range that you might have might be something like this. Suppose h of x is equal to the function e to the x cubed. Okay, well, you got to remember a little bit about e. E is one of those excited functions that starts out hugging the x-axis, going through 1, and then shooting up to infinity. Okay, it gets really excited really fast. It's an exponential. The domain of that is all real numbers. The range of that is all y's greater than 0 but not equal. Okay, does not ever touch the x-axis. So if we're going to find the inverse for that one, our work would be e to the, instead of x cubed, it'll be e to the h inverse cubed, and x would be on the other side. And we would need to work towards, you know, getting rid of some of the things there. All right, so the first thing we want to get rid of is the e. Do you remember how to do that? You know how to get rid of a square with a square root. How do you get rid of an e? A natural log, right? Okay, a natural log. All right, so we're going to apply a natural log here to x, and we're going to apply a natural log to the function that has e, h inverse. Now it gets kind of messy. Okay, pause. Okay, the rules for natural logs are fun because this always gets pulled to the front when you have a natural log. And so we'll have the natural log of x. We'll have now h inverse of x cubed pulled in front of the natural log of e. And the natural log of e is linear, and it has a value of 1. And so that simplifies our equation down just to h inverse of x cubed, and we can apply the cube root on both sides, which does not need a plus or minus. And we now have h inverse of x by itself. And so the cube root of the natural log of x, and the domain and the range would be the reverse of the original domain and range. And so the range is now all real numbers, and the domain is now x greater than 0. Okay, all numbers greater than 0. Okay. All right, the very last one we may not finish. And if we don't, you could watch the little video to learn how to do that. But this is a really common equation in calculus, but it kind of stumps people on how to solve it. Solve that problem. To solve means to get x all by itself. Okay? All right. So what I want to show you is what negative means. Okay, what does that 5 to the negative x, what does a negative exponent mean? It's a 1 over. So this would become 1 over 5 to the x. That would be the first step, is to make that a fraction. The second step is to get rid of the fraction. Okay, if you can have the chance to get rid of fractions, that's going to be the best option for you. So you're going to take this entire problem and multiply it by the number 5x. What's 5x times 5x when you multiply those two together? And it's not 25 to the x, so don't say that. But what's 5 to the x times 5 to the x? 5 to the? It's x plus x. Because when you multiply, what do you do with the powers? You add them. All right, plus, and then 5 to the x times 1 over 5 to the x. We're distributing here. Okay, we're distributing this all in. That just becomes 1. And then on the far side, we have 3 times 5 to the x. And please don't tell me that's 15 to the x, because it's not. It's just 3 times 5 to the x. All right, so we've got, oh, we ran out of time. So we have 5 to the 2x plus 1 equals 3 times 5 to the x. All right, at this point, this is where, so far, I think everything you've seen, you've seen before. Here's where something might be new that you haven't seen before. First of all, if we write 5 to the 2x differently, you can write 5 to the x squared. That's the same thing, because remember, you're just multiplying exponents. All right, so that would be one thing. And then the other thing is something called a substitution. Let's substitute the letter a for the expression 5 to the x. And so everywhere we would see 5 to the x, which would be here and here, let's replace that with the letter a. So now we're going to have a squared plus 1 equals 3a. That problem is a quadratic. A squared minus 3a plus 1 equals 0. Do you recognize that? That's a power 2 problem. That's a quadratic. That means it could be solved with the quadratic formula. So a equals plus or negative b, so that's negative negative 3, plus or minus the square root of b squared, so negative 3 squared, minus 4ac all over 2a, so 2 times 1. So a equals 3 plus or minus the square root of 9 minus 4 all over 2. So a is 3 plus or minus the square root of 5 over 2. But what did a stand for? Remember, we just said that a stood for 5 to the x. So if a equals 3 plus square root of plus or minus square root of 5 over 2, then 5 to the x must also equal 3 plus or minus square root of 5 over 2. And we can apply a natural log to both sides to solve for x. So x is the natural log of the quantity 3 plus or minus the square root of 5 over 2. And that would give us two answers that would solve this quadratic problem. These answers, of course, are going to have decimal approximations, but the way we've solved it, we have the exact, accurate answer without needing to use decimals, but using the elegance of a natural log and the quadratic formula. So that's kind of a interesting and challenging problem, and there's, I think, 2 of those in your homework, so hopefully you're able to kind of follow that strategy and apply it to those problems.